Hello guys, welcome back to Maths on African Motifs, still on our Mathematics N6. This is question 5 of November 2022 exam, but in this case, we want to focus on the part of the volume and the part of the volume moment, which is the application of the center of gravity, all right? So that's the typical question that we're gonna have, and want to just talk about this and understand how the questions are given. How are we supposed to attempt such typical questions? So the first part is our N5. Like I always say, this first part here that you have is your N5, all right? The calculation, the sketching of the graph, this and that is our N5, N4. They want you to go back to those N4, N3 sketching of graphs, all right? Then the calculation of the volume is the one that we have in N6. Yes, we had this part in N5, but in N5, we only focused on one type of calculation of the volume, and we ended there. So this is going to be a continuation. So I'm not going to waste much time on this first part of the sketching of the graph. Like I said, this is our N4. Let us also try to visit our N4 for the revision of the sketching of graphs. So given, make a neat sketch of the graph of y is equal to sine of 2x, right? So that's 5.11. We need to sketch the graph of y is equal to the sine of 2x. Show the representative strip or the representative element that you will use to calculate the volume if the area bounded by the graph and the ordinates y is equal to 0 and x is equal to pi over 2 rotates about the x-axis. So the volume is the one that is going to rotate about the x-axis. That does not mean your representative strip is supposed to be in the x-axis. No, the representative strip is supposed to be determined by the limits that you are given. All right, so we want to draw this graph bounded by this, meaning to say up to from x, we're gonna have, remember, this is from in them bounded by the line, which is y is equal to 0, which is our x-axis in this case, and also x is equal to 2. So this was supposed to be taken on a condition of x. The coordinates of x are the ones that we need. X is equal to, and x is equal to pi over 2 as our limits, all right? As our limits. Remember, the graph of sine is not limited. It can be like this, right? That's the graph of sine, and so on and so on and so on. So like I said, you need to understand the sketch, how the sketch of the graph of the sine look like. Then from there, how do we sketch it? All right. So we know that the graph of the sine, like I said, is supposed to look like this, right? But taking a consideration from 0 to pi over 2. Remember, pi over 2 represents 90 degrees, 180 divided by that's 90. So before the pi over 2, it means there is a pi over 4 that we can also take advantage of. Half of this, half of pi over 2 is pi over 4. So you can also take a closer look before that, so that we can at least have 0, pi over 4, then the pi over 2. All right. We know the graph of sine, when it is given as sine x, right? Not to, this is sine 2x. When it is given as sine, as here, it's 1 sine x, it means it is going to be taken at maximum value at 1 and the minimum value taken at what? At -1, right? So that is what you're going to have in this case. So this part, you're just gonna make a substitution and see at sine pi, at sine 0, you know that, guys, sine 0 is equal to what? Sine 0 is equal to 0. So this one is gonna be a 0, or we can just use our calculator. Let us see here. On our calculator, make sure that your calculator is in radians. Since these are radians, pi, these are radians. So substituting pi being a 0 in this case, so this is our x value. So you're gonna have sine 0, like I said, guys, sine 0 is 0. So this one is gonna be at this point. Then sine 2 times pi over 4. So this will be sine 2 times pi over 4 is pi over 2. Right? It's going to be like this because there's a 2x there. So it's 2 times pi over 4, like this. pi over 4. Just gonna have a sketch, all right, which is at 1. So this at 1, then pi over 2. When this is pi over 2, it is going to be at what? At 0. So this will be at 0 at this point of pi over 2. Then we can just join. So this is the sketch that we are having. Like I said, we are supposed to have the graph of sine like this, supposed to be a continuation. But in this case, we are limited up to pi over 2. So we're not gonna have that extension of our graph that side, but it was supposed to be there like that. All right. So on this graph, the other thing that we have here is that we are not told about the representative strip, that it is supposed to be perpendicular or it is supposed to be parallel. We are not told. We are told that the volume is going to rotate about the x-axis. This here, I said, it does not affect our representative strip. Our representative strip is going to be affected with where you have the limits of the function. As you can see, according to this graph, it is best for us to use the limits 0 to pi over 2, which are the limits for x. So if we are using the limits for x in this case, what does it mean? It means we are going to take our representative strip on those limits of x. So it is going to be represented in the x, right? So we're going to have it is of best suit. I'm not saying if you use the representative strip in the y, you're not going to have, no. You are going to have the same, but the format or the formula for the volume is going to differ. In N5, we're dealing with this. In N5, our representative strip, if it was for x, you were calculating Vx. That is what we knew. If our representative strip was for y, you were calculating Vy. But in N6, guys, we have what we call the shell method. The shell method, it opposes that. If your representative strip is like this, all right, and you are given your axis of rotation in the y-axis, they are parallel to each other like that, right? The representative strip is for x, but your volume is taken in the y. It means you can calculate that volume with the representative strip for x, but you have to use the formula for the shell method. All right, we're going to explain that later on. But I'm saying the representative strip, this is what I'm trying to say. The representative strip, this here, is not affected to say it was taken like this or like, no, it's not affected like that. It is of best suit of the question if it is not given. This is not a controlled question. We shall say what we call controlled questions. Those ones you'll be given, your representative strip is parallel. It's perpendicular to this. That one, you use as it is. So this one, it's for choice. So here it is best of suit to use these limits in the what? In the x. So we can use our representative strip in the x so that we do not struggle in any other calculation that can happen. All right, so that is our graph in this case. So that is how your graph was supposed to be like. So we said this representative strip was of best choice, not to say if there's some way that limited us to take that. No, it's not like that. All right. So with this we've got, so that's why you have 2 marks here. They are saying you know these graphs from your N2, from your N3, N4. We had these graphs of sine, cos, every type of a graph. N4, that was, remember N4, there's a question that only talks about sketching of graphs. So they expect you to know that. That's why the marks is just 2 marks. So I will expect you to revise on your N4, just have a recap there. All right, 5.12, sorry. I don't know what's happening with this software. I don't know, sorry for that, guys. 5.12, calculate the volume generated if the area described in question 5.11. All right, rotates about, it is still rotating about because, guys, we were told that this area that we are talking about, its volume, all right, is going to be rotated. It is going to rotate about what? About the x-axis. And this is what you're given. It is rotating about the x-axis, and we're supposed to calculate the volume. All right, so this is what you do. You have to check first because these are 2 things that we are supposed to consider, formulas for the volume. All right, so that's 5.12. So this is what you check, because it's either for volume, you are going to use a disk method or you are going to use the shell method. All right. Where do we use the disk method? If the representative strip is perpendicular to the axis of rotation, we use a disk method. If the representative strip is parallel to the axis of rotation, we use the shell method. All right. So in this case, if we take this is our representative strip here, and the axis of rotation is the x-axis. So what are they here? Considering your representative strip here, this one, and your axis of rotation, which is the x-axis. How do you call these two, the combination of these two? Are they perpendicular to each other or they are parallel? These two lines, they are perpendicular. They are at 90 degrees to each other. The representative strip and the axis of rotation, which is the x-axis, they are perpendicular to each other. When they are perpendicular to each other, we use the disk method, right? Please be careful there. We use the disk method. And which part are we referring as the disk method? We had that part on our notes on the volumes. These are the volumes that we have in this case. In terms of the disk method, I explained that we are going to use this part here, all this part that we have here. All right, all this part here is for the disk method. All right, this one is for your disk method, and this part that we have on the other side here is for the shell method. All right, this one is for the shell. So we are calculating the volume with respect to x. That is what we are given there. And our representative strip against, so we're going to use the disk. And there is just a single curve that we are given. So this is the formula that you're going to use. Vx is equal to pi, the integral of y squared dx. All right. If there were two functions, then we use this one where we are subtracting the upper minus lower, okay, which is the same thing as this part. This one is for the y. But for the disk, I mean, for the shell method, this is what I was explaining. You'll be having the volume according to x, but the representative strip will be for y. Right? The representative strip will be for y. Right? We shall talk about that. But this one, it was a shell. It was a disk method. Why? We said the representative strip that we are given here is perpendicular to the axis of rotation, which is the x-axis. So if it was a condition that they wanted us to calculate this about the y-axis, let's say they said about the y-axis like this, it means this was what happened. We have got the y-axis, all right? This is it. This is our y-axis. The representative strip is this one. Remember where your representative strip is. This is your representative strip. So it means at this condition, you were going to take a consideration to say these two that we are having, they are saying when it is about the y. So you're taking the y-axis and your representative strip. How are these two connected? They are parallel to each other. So these two lines will never meet. They are parallel. So on that condition, you use the shell method. All right. But like I said, in this condition, we are going to apply what? We are going to apply the disk method. All right. So that's it there. All right. Because this representative strip is perpendicular to the axis of rotation. So there, I'm going to use the disk method. So using the disk method. So what does the disk method state? State that the volume that you're going to calculate with respect to x, we saw that from our formula sheet on page 5 of your formula sheet, all right, is given as pi, the integral of, given the limits a to b of y squared dx. So that's it. This is the disk method is the method, that was the method that we're using in what? In N5. That was your method in N5. So you see that there is nothing new on this part. This is our N5 as it is on this one. All right. So that means our Vx is going to be pi, the integral of, take our limits from 0 to pi over 2. Then this is y squared. What is y squared? This is the function of x. Y here represents f of x. which is y, is equal to sine of what? Sine of 2x. So this will be sine squared 2x with respect to x. So we need to integrate this, substitute our limits, and as you know that whenever we're given this pi and so forth, the trig function must be in radians. So how do we integrate a sine squared? Yes, we can use the identities. Remember, we talked about this, that whenever in our integration, I want you to go back to the integration of trigonometric function. We talked about the integral of sine to the exponent of ax dx. When this is an even number, where this is squared, we are going to use the identity for sine squared. That is, remember, that sine squared ax is equal to 1/2 minus 1/2 cos 4ax. So this is 1/2 cos 4ax. Remember our identity. So we can use this identity to integrate the sine, or we can use, in this case for sine squared, we can just take our formula sheet, right? Our formula sheet, the integral is already there, right? So this one under integrals, right? Remember, this is the column for integrals. These are derivatives here. So they are saying the integral of a sine squared ax is given by this formula. This is how integrate. So you can use the formula instead, x/2 minus this, because we have the formula there. So instead of us breaking into identities, instead of us applying this identity is best to use when it was a sine to the exponent of 4. But for sine squared, I explained even on that introduction of our trigonometry that there's no need for us to do that. So here we are going to just apply the integral straight. We are told that on that part, the integral of sine squared ax like this with respect to x. So we are now taking the formula that is corresponding to there. We are given that it's x/2 minus sine 2ax like this over 4a plus c. This is the formula for the integral of a sine squared. So meaning to say here, we can simply find our answer direct. The volume with respect to x is going to be pi times the answer that we get after integrating this. So the answer is supposed to be x/2. So you're going to have x/2 minus sine 2ax. So this is ax, our ax, which is 2x. So here we are now having 2ax. So meaning to say we multiply this by 2. So 2 times 2, that will be 4x. So this will be 4x over 4a. A is the coefficient of x. That this a here is the coefficient of x. This is x, the coefficient of x is what? It's a 2. So that is going to be 4 times 2. That's 4a. 4 times a 2, which is what? Which is 8. So this will be over 8 plus the constant of integration. But there we have got limits. So there's no need for us to apply what? To apply the constant of integration. So that's it. We could just have used our integral straight from the formula sheet. But if we were to use this, it's fine. We're going to apply this identity sine squared, this meaning to say, when we are given sine squared 2x, it is going to be 1/2 minus 1/2 cos. This is cos 4ax, taking it cos 4ax. What does it mean when you're saying cos 4ax? We are multiplying ax by what? Ax by 4. Our ax here, ax, which is 2x, multiply that by 4. So that's 4 times 2, which is 8x. So it's going to be cos 8x like that. All right. Then from there, we find the derivative that corresponds to this part. All right. We are now finding the derivative that is corresponding to this part. All right. That is the idea. But in this case, we could have, the integral that is corresponding to that part. But in this case, guys, why do you have to struggle when there is a formula that corresponds? So there you write down your formula, you substitute in your formula, you are done. You obtain full marks. You obtain full marks for that. All right, so that is the integral. So you see, guys, you just be afraid of this question. There's nothing. You just have to follow the steps. So this is it. Then the other mark that they need is the substitution, which is another thing that most of us, we just write the answer. We do not make. They want to see the substitution. So this is going to be pi into, in place of x, we are going to have a pi over 2. So this is simply pi over 2 like this, minus sine 4x. So this is sine 4x, guys. 4 times pi over 2 like this. This will cancel and to be 2 pi. So this will be sine 2 pi instead. Sine 2 pi over 8 like this. All right. That's for the upper limit minus the lower limit. This is a 0 here. X over 0 is 0 over 2. And also, you know that sign of a number, sign of a 0 is a 0. So this would be 0 minus 0, unless you can just substitute here. But I think by now, understand the sign. It's different from cos. Cos 0, remember that cos 0 is equal to what? Cos 0 is equal to 1. So meaning to say, the only part that we were going to simplify was this part, because this part, on the other part, there it's a 0. So let us see. Let us just try to make our substitution on the calculator. So this is, we are going to, we can even simplify this part under the bracket, and make sure that your calculator is in radians, right? Like I said, make sure that your calculator is in radians. So we've got a fraction there, pi over 2. So this is pi over 2 like this. All right, divided to 2. Okay, minus sine 2 pi. So this is sine 2 pi over 8 like this. So close this bracket, you're gonna have 1 over 4 pi. So that is pi into 1 over 4 pi. Remember, this is a 0 here. There's nothing there. It's going to subtract a 0. So this will be 1 over 4 pi times pi is simply 1 over 4 pi squared. So it's simply pi squared over 4, right? This one is same as 1. So pi and pi is going to be pi squared 1 times, which is pi squared over 4. So that is our volume. And remember, volume is measured in what? Cubic units, right? So you can have your volume this way, or you can even write this as a decimal, all right? So our volume can be expressed as a decimal, or gonna have our volume as, like I said, if you multiply this to pi, so you must multiply to pi like this, as a decimal, that's 2,467, all right? Or you can just round off, shift, set up, fix this to 6, then to 3 decimal places, you press 3. So round off your answer to 3 decimal places, which is going to be 2,467. So this will be 2,467 cubic units, or you can just write it that way. So that is the application of our volume. We talked about this, guys, the volume, how to calculate the volume from different methods, whether you're dealing with the disk method or it is the shell method that you are referring to at that moment. What you need is the formula. That is the best thing. And I showed you the formulas, which one to use for the disk and for the shell, and the conditions that make enables you to say you are now using the shell method. What are the conditions for that? All right. So that is it there. Let us check the question that is following, because this is a follow-up question. I'm going to just remain with this. On 5.13, they're saying calculate the volume moment about the y-axis as well as the distance of the center of gravity from the y-axis, again, from the y-axis, meaning to say, what are we calculating from the y-axis? We are going to calculate the x coordinate. If it is from the y-axis, you calculate what? You calculate the x coordinate, which is x bar, which is simply the volume moment about the y over the volume moment that we calculated. Anyways, let us get to the question. Remember, we want to calculate the volume moment about the y-axis. So this is what you're going to have. I want us to get to the formula sheet first so that we understand each other on this part. All right. Okay, going far here. I want this one. So this is what I want you to see here. We are calculating, we are talking about the volume, all right? So we need the volume moment. So we are going here on the volume moment and also the center of gravity. This part here, they are saying the volume moment is equal to, depending, this is the volume moment for the x, the volume moment for the y. All right. So there we are talking about the volume moment about the y. So we're talking about this one for y, and also the center of gravity from the point, from the y-axis, meaning to say our x, we are going to use this formula. X bar is equal to the volume moment over the volume. All right. The volume moment about the y, this is what we have here. All right, let us take our formula. I'm going to talk about this formula, what it is representing. So we saw that the formula there for the volume moment, that's 5.13. The volume moment about the y is given as, we are given as integral of AB. This is R dV like this. All right. So this R here, it's best that you take this as your representative strip, all right, to say our representative strip here is for what? It's for X. We are given our representative strip representing what? Representative X. So our R for this is going to be equal to X, okay? Then dV as the expression of the volume expression before we integrate, before we wrote the expression for the volume, there we have the dV before integrating. Remember this here, right? Let me explain it this way. I'm gonna take it back on top. This one, dV, it is the expression of the volume that you had. It's a continuation of the volume that you calculated. And this is what we have. The expression before the volume, the dV is represented by pi y squared dx. Okay, this is what we have before. dV is equal to pi y squared dx. We integrate both sides as we know so that we obtain the volume. So the V is going to be equal to this integral of pi y squared dx with the limits a and b, where we take this out of the integral of the pi. So meaning to say the dV is it represents the volume expression before, which is pi y squared dx. So wherever you see, you take the volume of the previous question, right? It's not a fixed formula that you're going to have to say this one you take from because it's from that volume that you calculated before. So you work from that volume. So this one is simply our volume expression, all right, from the previous question that we had. So meaning to say your volume moment with respect to y is going to be the integral of our limits a and b. We said R represents the strip of x. So this is our representative strip in the x pi. There are adjustments that can be made if you're dealing with the area moment, not on volume. So on volume, just take the R representing what? Your representative strip as it is. Then this dV as your volume expression as it was from our previous question. We said the volume expression is given as what? As this pi y squared dx before the integral, all right? Before the integral. So this will be pi y squared dx like this, all right? So from this, we can take our pi out of the integral. So this pi here, we take it out of the integral. We've got a and b of x. So this will remain with y squared dx. So that is what we are going to have for our volume moment. So that's pi, the integral of, we can substitute a and b, does not change. Those are the limits that you used before, the a and b that you had from 0 to pi over 2 as it was before. So that's 0 to pi over 2. And this x, it's a variable. There's no substitute for this x, right? There is no substitute for x. It's just x as it is, all right? From our representative strip, I said for volume, just take the strip that you used before, it's for x. So you use that as your x, R for x, times y squared. Like I said, this is your, guys, it's a continuation of the volume that you had before this one. It's not like we are having a new question, this one. This one, because whatever that you're going to have as the center of gravity, it is going to be the volume moment over the volume that you calculated before. So it's a continuation. You use that the expression of that volume that you had before. That is the condition. So this was our expression for volume, pi y squared. And we took this pi and we said y squared represents what? Sine squared x as it was, because this is our y, which is equal to sine to x, and it gave us sine squared to x. So that part is not going to change, right? So this part of y squared is still our sine squared. So this is our sine squared 2x with respect to x. So the question is now in your hands. How are you going to integrate this? All right. So as we can see, we are back to our integration. That question of integration, we had the condition of this product of two terms, an algebraic and a trigonometric. We said on that condition, it is best for us to apply by parts. All right. If we were to apply by parts, I want us to be careful. In this one, it was going to be easy and difficult for us to work with it because remember, we are supposed to make substitutions and integrals there inside derivatives, isn't that? It was going to be difficult for us to work with this sine squared 2x. It is better to work with a linear, not to work with this raised to the exponent of 2. So what can we do before the application of by parts? Let us try to simplify this. Working with a linear, we can say that this here, guys, they can even give you a question like this on question number 2. Remember that question number 2 on integrals. They can just give you that y is equal to x sine squared 2x and find the integral of y with respect. They can even ask you like this. It can be a question like this. So you're supposed to know, yes, by parts, we are supposed to use by parts, which is fine. But this sine squared is going to be difficult for us to work with because of the exponent of 2. So we have to look for an equivalent identity for sine squared. Remember, from the integrals of sine and cos, we talked about this identity. Sine squared ax being equal to 1 over 2 minus 1 over 2 cos 4ax. I even talked about this. Is it 4 or 2? This is 2ax. Guys, the previous case, I think I wrote like 4. Guys, if I wrote 4, please, can you correct that? Can you correct that? It's supposed to be a 2 there. So I want you to correct that. This is 2ax, all right? Then if it is for cos, I want you also to cross-check with our integration, the one that we did, all right? So if it is cos ax, this will be 1 over 2 plus 1 over 2 cos 2ax again, all right? This is ax, this will be 2ax, all right? So I want you to correct that, but please, guys, and please, let's do so. If I wrote, I'm thinking like I wrote a 4 there. I'm just like, I don't know. It's maybe because I was keeping in mind of that integral of that sign. It was having 2ax and also having a 4a. So I was just like having that 4a in mind, maybe. All right, so this is at least a linear that we can play around with. We are dealing with a sign. So the second one is not valid because it's for cos, but I just want you to know because next time they will give you a cos squared there. You use that one that I wrote, okay? So here we're going to have sine squared x to this one as it is going to be, instead, let us substitute here direct because we want this linear. So this will be pi, the integral. We are not integrating here, guys. We are not yet integrating. I said, let us first rewrite in a way that is easier for us to work with. So this will be half of, so you're going to have half minus a half for this sine squared 2x. So this is cos 2ax. 2ax meaning to say we're going to multiply our ax as it was. This was our ax, which is 2x. But this time we are multiplying by 2. So it's 2 times 2x, which is going to be a 4x. So this is cos 4x like this. All right. So like I said, guys, if I used a 4 in the previous case, please, can you correct that? This is 2ax. So this is what we have. At least there we've got a linear. So we still have our by parts, but still we having that by parts in mind. There's something that just happened because here you can see that we now have brackets, this and that. So we're going to expand. So the by parts for now, let us just forget about it. We're going to use it later on. So here we can expand, all right, by x, which is going to be x times half, which is half of x. So this will be half of x minus by x here. This will be half of x cos 4x like this with respect to x. So this is what we have. And in this case, half is actually common. It's a constant. So you can take it out of the integral, right? Out of the integration sign. So meaning to say, if we take this half, it is going to multiply with a pi. That's pi times a half, which is going to be pi over 2. The integral of So you'll be left now with x minus, if you factor out 1/2, you'll be left here with x cos 4x, like this, with respect to x. All right, now we can integrate. But in our integral, yes, we had a by parts and we still have that by parts. But the first part, there's no need for us to apply by parts on this x here. There's no need there. We can just integrate was the single term that we have. Remember, this is to the exponent of 1. We just have to add 1. So it will be x squared over 2. So there we are going to have x squared over 2. But now we are going to have x cos 4x, this one, which is a product of two terms, an algebraic and a trigonometric. So there we do not have any way. We have to apply that our by parts. So that is where now we can have. So this one, we're supposed to use by parts, but we see that sine squared, there's to use that, we use at the identity. In application of the identity, there are brackets there. So you can't ignore that because you have by parts in mind. It will come to that extent. Here we have our by parts at what? X cos 4x. We just want to integrate this only cos x cos 4x, this one, this part alone. All right, so let us have it here. So the integral of x cos 4x with respect to x from our by parts, remember, our by parts formula is supposed to be the integral of f of x g prime dx is equal to f of x by gx. So this is f of x by gx minus the integral of f prime x gx dx. All right. So we need f of x that we are going to use to determine the first derivative. So if we let our f of x to be x, that means the first derivative will be a 1. Then the g prime will be the remaining part of cos. So this will be cos 4x. So we've got cos 4x there. Okay. Find the integral so that we've got our gx. So gx is going to be cos 4x. Remember, the integral of cos, it's a sine. So this will be sine 4x over a 4. Okay. Remember, we have to divide by this term. Sine cos ax, it's sine ax over a. So this is our a here. So we're going to divide by this. So on the formula, we're saying the integral of the whole of this part of x cos 4x is going to be given as what? It is going to be given as f of x by gx, which is our f of x. That's x by gx, which is sine 4x over 4, minus the integral of the first derivative, which we got here, it's a 1. So this is 1 times gx dx, which is our gx here. It's a sine 4x over 4 with respect to x. Okay, so meaning to say on this part, we are now supposed to integrate the last part. So here you can just write maybe as a single term, just write as x sine of 4x everything over 4. This is same as over 1. All right, minus, we can take 1 over 4 out of the integral so that we can integrate properly. So you remain with the integral of sine 4x there. And what is the integral of sine 4x? Remember, sine changes to a cos. So it's negative cos 4x over the 4 for the integral. All right, then we're going to combine this x, sine of 4x over a 4, minus and a minus, that's a positive. So you're going to multiply 1 times cos 4x, which is cos 4x over 4 times 4, which is 16. So yes, we've got the cost of integration, this and that, but forget about that because we are still working out our question. So this is the integral of what? Remember what we are talking about here, guys. We have to be very, very careful in our simplification. We have to be very, very careful. What is it that we are talking about? We are talking the integral of this. This is the whole part is representing the integral of x cos 4x, this one, x cos 4x. All right, that is the whole integral that we are talking about there, x cos 4x. So now it means in place of that x cos 4x that we have, we are going now to substitute with the answer that we got. All right, we are going now to substitute in place of x cos 4x here, in place of this integral x cos 4x. But remember, there is already a negative that we have here. We are supposed to subtract whatever answer that we are going to get from this integral of x cos 4x, and this was the integral of x, or whatever that we had here. And we got this solution here. I'm just going to write the answer that we got here. We said it's going to be x sine 4x. So here we are going to have our answer on our final solution, which is x sine of 4x everything over 4, all right, plus cos 4x everything over 16 like this. So this is what we are going to have after the integration of everything, and not forgetting that we have got the limits there from 0 to pi. So we've got limits taken from 0 to pi. All right, so that's it. So all this whole part here, it was for us to be able to integrate, just to be able to integrate this x cos. So you see now, those formulas, those topics of integration as a separate topic, you must know that this is just an application. All right, so we can simplify further, then apply our limits. So that's pi over 2 into here, we're gonna have x squared over 2 minus times this is gonna be minus x sine of 4x over 4, right? Minus times a cos, which is gonna be minus cos 4x over a 16 like this. Then our limits pi to 0. All right, so if we are to check here, all right, this is pi over 2, not pi over 2, pi over 2, the limits there. It's a pi over 2 here, pi over 2, pi over 2, pi over 2. All right, like that, pi over 2, pi over 2, pi over 2, right? That is what we had. All right, let's just stop here. We had the same thing. All right, yes, pi over 2. Okay, so this part, this one is fine. All right, no problem. So that is it here. Now at this stage where we are here, we are supposed to make sure that you have your substitutions properly on this part. All right. So if you check this one, we can just substitute direct in place of our x. All right, that will be pi over 2 here. So we're gonna have this as pi over 2. In place of x, we're gonna substitute pi over 2. So this is simply pi over 2 squared. That's our upper limit, all right, over 2 minus our x, which is x pi over 2. So that's over 2. Then we have got the sign, in this case, of 4 times pi over 2. Remember, when you open the bracket on your calculator here, it's gonna open a bracket. Your calculator automatically opens the bracket here. All right, so it will be 4 times pi over 2, everything over 4, minus the same thing on cos. If you write the cos, it opens the bracket automatically. So you're gonna multiply with our x, which is pi over 2 there. So that's pi over 2 in place of x. So this is it over 16. All right, so this is a single term, this is a single term here, minus, you do the same thing on a cos. You're gonna substitute, on the lower limit, you're gonna substitute the lower limit to be a 0 here. Guys, 0 squared, that's a 0. Minus 0 times here, x is multiplying a sign, and also sine 0 is a 0, so that's a 0 also. But cos 0 is 1. So this will be minus 1 over 16, like this. All right. So that is what you are going to have. So I was actually checking also around your memo of this question paper. They just made some of the mistakes in the substitution. If you substitute here, 4 here on sine, this is sine 4x. So if you substitute pi over 2, like you want to do it stage by stage, you substitute like this, 4x like this, which is 4 times our x, which is pi over 2. It is going to be 2 into 4, which is 2. So it is going to be sine 2 pi, not sine pi. It is going to be sine 2 pi. That was the error that happened in your memo. They used sine pi instead of sine 2 pi. It was just a mistake there. All right, so you simplify everything, guys. Here we need our calculator. I showed you guys how to use the calculator. always. So you're gonna press in your values, everything. So I just want you to start with this one so that we'll be clear that we are moving together. I want you to start with this one here. To simplify this and make sure that your calculator is in radians, you'll get something like 1,171. All right, minus here, if you simplify 0 minus 0, that's a 0. 0 minus 16 is going to be minus 1 over 16 like this. So it will be minus, which is a plus. Then you simplify everything, you're going to get something like 1,938 units to the exponent of 4, since we are working with what? With the volume moment. So I said, check, if you check your error there, your formula, your memo is just a slight mistake that happened on the substitution part. Everything, it was fine. They worked out everything fine. But on the substitution, they just made a mistake. So it can be like that. All right. But this is what's supposed to be our answer in this case. All right. This is how we are supposed to properly substitute this on your calculator. All right. So that is our volume moment. But the question was not just ending on the volume moment. They also wanted us to have this x coordinate here. All right. Remember, they are saying also we are supposed as well as the distance of the center of gravity from the y-axis. So the distance of center of gravity from the y-axis, that is the distance of x. So it's the x bar from the y-axis, that is x bar. All right. So you use the volume. Remember, here we have got the volume moment for y that we calculated. So that one, the center is simply taken from this y, also from your formula sheet. Let me show you so that next time, even if okay, here we talked about this. We said x bar is the volume moment according to the y, or for the y-axis, over the volume that we calculated before. That is the idea of the question. All right. So this one is simply x bar is equal to the volume moment in y over the volume. So that's why I said this one is a continuation. The volume moment that you calculated, the volume that you calculated corresponds with the volume moment that you just calculated now. So our volume moment, we got 1,938. So the volume moment is measured in units to the exponent of 4 over the volume that we calculated. Remember our volume, so we're just going to take our volume as it is, and our volume here, it was 2,467, or this pi squared over 4, or 2,467 cubic units. All right, so this is 2,467 cubic units. So if we divide by 2,467 cubic units, it means our answer is going to be in units. This 3 and 3, so our answer is going to be in units there. So this will give us something like 0,786 units. All right, so that is our distance from the y-axis. Okay, so I just want us to try by all means. If it was the distance from the x, it is going to be y bar, all right, from the y-axis x bar. So I want us to try as much questions as we can, just try to revise, have a recap on this part of the volume and the volume moment. We shall have similar questions or more questions of this nature, so that you'll be able to also tell how do they ask these questions on volume moments. But that is how you answer your questions, also with the help of the formula sheet. I explained, I'm going to explain much as we have other questions, but I think with the little information that we had from the formula sheet, you can use it to answer another question similar to this, whether it's for the y-axis or for the x-axis. The volume moment for the y is RDV. R, take it from the strip that you used before. What is it representing? Is it x or y? All right. Then I said there are adjustments that you're going to talk about there for area. All right. But for dV, the volume expression that you had, you take that expression. If it was another expression, maybe you use that, what you had before, guys. You use what you had on your year. So I'm not saying this is this formula that I wrote here Here it's a fixed formula. The fixed formula is the format of the formula, this one, the format. What is there? The format. That's the fixed formula, the format. That is what matters, the format. Then after that, what does it mean? How do you substitute? Because this is what determines what comes later on, your volume expression from the previous question and your representative strip. So like I said, we shall see more questions that will explain of this nature.